Understanding quantum mechanics. Quantum mechanics is essential to understanding the behavior of systems at atomic length scales and smaller. Quantum theory claims that reality is not continuous, but rather granular and discrete. It is not possible to zoom into the fabric of reality like zooming into a Mandelbrot equation and keep seeing patterns. Eventually, the pixels of reality are reached, and in between the pixels there is nothing. There can be no other alternative to reality. If reality were continuous, infinity, a concept that exists only in mathematics and imaginations, would be needed. It is no wonder that when we zoom into reality, until its pixels are reached, we observe paradoxes like the wave-particle duality of energy and matter as manifested by light. Everything becomes statistical and probabilistic instead of deterministic. Reactions can happen spontaneously without any actions to cause them. Particles suddenly appear from nowhere just to unexpectedly disappear as if they were playful dolphins. Atoms suddenly break apart without any reason as if they had alarm clocks inside them to wake them up. Reality becomes uncertain and philosophical where observation of a process affects the process itself, like animals in labs with too many probes attached. Two properties of quantum objects that seem paradoxical are superposition and entanglement. Superposition is observed when a quantum object is found to be in more than one place at any one time and or with more than one state at any one time. This can be visualized in a propeller that spins very much faster than what we are able to perceive. The spinning propeller, which is in reality a stick, seems to occupy every position on the perceived disk. Similarly, quantum objects display superposition if they move from the position here to the position there very much faster than the light travels. Entanglement is when two quantum objects in two different places and or states behave as one object. This phenomenon can be understood if we regard the two entangled quantum objects as one object that is moving between the two places so fast that it displays the superposition property explained before. Using quantum theory, quantum computers, which could be exponentially faster than classical digital computers, can one day be developed. Before digital computers, analog computers used variable levels of current to represent any numbers desired. The currents could not be kept sufficiently stable and accurate, and changing them was slow and energy consuming. Classical digital computers of today use currents with only two discrete levels. The transistors used as current gates can be either turned on or turned off to represent two discrete values of 1 and 0. Any number desired is coded with the discrete ones and zeros called bits. Quantum computers of the future will use photons and electrons that can have more than two discrete states called qubits. This can be visualized by comparing three locks that represent three computers. The three locks are unlocked by choosing an integer number between 0 and 1023. The analog computer of the past is represented by a lock which is unlocked by one key, where any numbers from 0 to 1023, theoretically an infinite amount, is selected by setting a variable current level to give an integer between 0 and 1023. The classical digital computer of the present is represented by a lock which is unlocked by 10 keys, each with two discrete levels. An integer between 0 and 1023 is binary coded using 10 bits. The quantum computer of the future is represented by a lock which is unlocked by one key with 1023 discrete states to give an integer between 0 and 1023. Because quantum computers use qubits that can have more than one state at any one time, they have the potential to be exponentially faster than classical computers. They will be able to break presently used encryption schemes that need an unrealistic amount of time to break with classical digital computers. Because it is impossible to copy data encoded in a quantum state, and the very act of reading data encoded in a quantum state changes the state, quantum computers have great potential for securing data communication against forgers and eavesdroppers.